In the heart of the Islamic Golden Age, a time of extraordinary intellectual and cultural advancements, one scholar's curiosity would resize the known world. His name was Abu Rayhan Al-Biruni, a polymath whose mind knew no bounds. Born in the year 973 in the outer district of Kath, the capital of Khwarazm, his journey began at the edge of a vast and changing empire. From a young age, his insatiable hunger for knowledge was apparent to all who knew him. He delved into mathematics, astronomy, physics, and medicine with equal fervor. His early life was marked by political upheaval, forcing him to move frequently. These travels, however, were not a setback but an opportunity. Each new city was a new library, each new encounter a new lesson. He mastered numerous languages, including Sanskrit, which would prove invaluable in his later work. His reputation as a brilliant thinker grew, eventually reaching the ears of the powerful Sultan Mahmud of Ghazni. Taken into the Sultan's service, Al-Biruni accompanied him on his campaigns into India. While the Sultan sought conquest, Al-Biruni sought understanding. He meticulously documented the customs, sciences, and philosophies of the Indian subcontinent. This work would become his magnum opus, the Kitab al-Hind, Book of India. It was during these travels in India that a profound question, one that had puzzled scholars for centuries, resurfaced in his mind. Ancient Greek scholars like Eratosthenes had already proven the earth was round. Eratosthenes had even estimated its circumference with remarkable ingenuity. His method required observations from two different cities located hundreds of miles apart. It also relied on the assumption that the sun's rays were perfectly parallel. Al-Biruni, a man of precision, wondered if there was a more elegant, more accurate way. Could the Earth's size be determined from a single location? The idea that sparked in his mind was a stroke of pure genius, combining observation with the power of trigonometry. He realized that the key lay in the relationship between the height of a mountain and the dip of the horizon. From a high enough vantage point, the horizon appears to dip below the true horizontal line. This dip angle, he reasoned, was directly related to the radius of the Earth. The theory was elegant, but its execution required a specific set of conditions. He needed a tall, isolated mountain that rose from a perfectly flat plain. He found the ideal location near Nandana Fort, in what is now the Punjab region of Pakistan. The fort was situated on a hill, and nearby stood a prominent mountain. The surrounding land was a vast, flat salt range, perfect for his measurements. His experiment would consist of two main parts. First, he had to accurately measure the height of the mountain. Couldn't simply climb it and drop a rope. Instead, he used trigonometry, creating a baseline on the flat plain. He chose a point on the plain and measured the angle to the mountain's summit using an astrolabe. Then he moved a known distance away from the first point along the baseline. From this second point, he measured the angle to the summit again. With two angles and the length of the side between them, he could calculate the mountain's height. This was a practical application of the law of sines, a formula he had helped to develop. The first, crucial piece of data was secured: the height of his observation point. Now, for the second and most critical part of the experiment. He and his team climbed to the very summit of the mountain. From the peak, the world stretched out below them in a breathtaking panorama. He waited for the perfect moment, when the air was clear and the horizon sharp. He then set up his astrolabe, ensuring it was perfectly level. He aimed the alidad, the rotating arm of the astrolabe, at the distant horizon. He measured the angle of depression, the dip of the horizon from the true horizontal. This angle was tiny, a fraction of a degree, requiring immense precision to measure. He recorded the measurement with utmost care. Now he had the two values he needed, the mountain's height and the horizon's dip angle. The rest of the work was not in the field, but in the mind. He constructed a geometric diagram of the situation. The diagram formed a right-angled triangle. The vertices of this triangle were the center of the earth, the summit of the mountain, and the point of the horizon. The side from the earth's center to the mountaintop was the earth radius plus the mountain's height. The side from the earth's center to the horizon was simply the earth's radius. Using the dip angle he had measured, he could apply the law of sines to this triangle. The formula, which is now known as Al-Biruni's formula, was elegant in its application. He meticulously worked through the calculations, his quill scratching on the parchment. The numbers resolved, the equations simplified, and the final value emerged. He had calculated the radius of the earth. From the radius, a simple multiplication by 2 times pi gave him the circumference. The result was astonishing. His calculated value for the Earth's circumference was approximately 39,968 kilometers. The modern accepted value is about 40,075 kilometers. His measurement had an error of less than 1%. This was an unprecedented level of accuracy for his time. He had achieved this monumental feat from a single observation point. His method required no long-distance travel or coordination between cities. It was a triumph of mathematics and scientific methodology. His work demonstrated a profound understanding of the planet as a sphere. Al-Biruni's achievement was not an isolated event in his career. He was a true polymath, a universal genius. He wrote over 146 books on a vast range of subjects. He developed new methods for determining latitude and longitude, compiled a detailed pharmacopoeia describing drugs and their properties. He studied the mechanics of springs and the density of gemstones. His anthropological study of India was objective and without precedent. He approached all subjects with a rigorous, empirical methodology. He believed in questioning everything and relying on evidence. His work on the measurement of the earth was largely forgotten in the West for centuries. It was rediscovered and translated much later, during the Renaissance. But his legacy in the Islamic world was immense and immediate. He inspired generations of scientists and thinkers who followed him. Al-Biruni died around the year 1050, leaving behind a universe of knowledge. His life was a testament to the power of human curiosity and intellect. He showed that with careful observation and the right tools, even the grandest questions could be answered. His elegant solution to measuring the earth stands as one of the great achievements in the history of science. A scholar who began his life on the fringes of an empire ended up measuring the very world he inhabited. The quest for knowledge was his lifelong pilgrimage. He treated the entire subcontinent of India as a subject of scientific inquiry. His approach was remarkably modern, emphasizing fieldwork and primary sources. He sought to understand Indian thought on its own terms, without prejudice. This intellectual empathy set him apart from nearly all of his contemporaries. Back in Ghazni, he constructed a massive observatory to chart the heavens. He meticulously recorded the positions of stars and planets, correctly proposed that the Indus Valley was an ancient sea basin. This geological insight was centuries ahead of its time. His mind could move from the vastness of the cosmos to the density of a single gem. He invented a specific pycnometer to determine the specific gravity of objects. His measurements of the densities of metals and minerals were incredibly precise. He was a pioneer in the field of comparative religion. He argued for a common human nature shared across different cultures. Sultan often consulted him on matters of state and strategy. Yet, Al-Biruni remained at his core a pure scholar, detached from political ambition. His true wealth was the knowledge he accumulated and created. The mountain he climbed was not just rock and stone. It was a stepping stool to the cosmos. The astrolabe in his hand was more than a tool. It was a key to unlocking celestial secrets. His calculations were not just numbers. They were the language of the universe made manifest. He confirmed the spherical nature of the earth with a new, powerful elegance. His method was a testament to the power of combining theoretical mathematics with practical observation. He understood that the universe was a book written in the language of mathematics. The flat plane was his canvas, the mountain his easel. He saw the hidden geometry in the landscape. His assistants looked on in awe, witnessing the birth of a new scientific principle. The measurement of the dip angle was the linchpin of the entire endeavor. A slight error in that single measurement would have thrown off the entire result. His steady hand and sharp eye were as crucial as his brilliant mind. The calculation itself was a multi-step process involving several trigonometric identities. He essentially created a right triangle in his mind, with the Earth's radius as one of its sides. By solving for the sides of this triangle, he could deduce the size of the entire planet. This intellectual leap was monumental. He had effectively used a small, local measurement to grasp a global dimension. His work was a quiet revolution, carried out with parchment and an astrolabe. He did not need to sail around the world to know its size. The world's measure was hidden in the angle of a glance from a mountaintop. This insight remains one of the most beautiful examples of scientific reasoning. He was a master of synthesizing knowledge from different fields. He used his astronomical knowledge to orient himself and his instruments. He used his mathematical prowess to devise the formulas he would need. He used his practical skills to conduct the fieldwork with precision. This holistic approach was the key to his success. Even in his final moments, his curiosity did not wane. A neighbor, a jurist, came to bid him farewell. Al-Biruni, struggling to speak, asked him to repeat a solution to a complex legal problem. The jurist, surprised, asked if it was truly the time for such matters. Al-Biruni replied, "Is it not better to leave this world knowing the answer to this question than to leave it in ignorance?" He learned the answer, and shortly after, he passed away. This story encapsulates the spirit of a man for whom learning was as essential as breathing. His legacy is not just in his results, but in his relentless, questioning spirit. Abu Rayhan Al-Biruni, the master, had proven the world was round and, with stunning precision, had taken its measure